All right, good morning. So here we are yet again for yet another lovely session of MENG 3310 Fluid Mechanics. This will be lecture 9 in the series, and today we're going to continue with a few examples of working with the Bernoulli equation. So we went over the derivation of the Bernoulli equation last time. We reviewed through a few of the simple applications of it, and we also looked into how to reconceptualize it as an exchange of energy, where, again, as a review, let me kind of backtrack a little bit and review how we can sort of think of this. So, Bernoulli revisited. Just as a review, what do we mean by Bernoulli and energy considerations? So we're working with Bernoulli more this lecture, and then in the following lecture, in lesson number 10, we'll be continuing on with new material, beginning our discussion of control volumes and such. So again, it represents an exchange of energy between velocity, or I should say kinetic potential, specifically gravitational potential, and pressure. Energy is expressed in all of these things. Energy, again, is expressed in all of these things, but the equation represents an interplay and a conversion between these. So again, if I have the formula, the general formula that we'll be using is P1 divided by gamma plus V1 squared over 2G plus ZA. This again is the Bernoulli equation, Z1. This is the Bernoulli equation stated as in terms of height, P2 over gamma. And there's many ways to express this. You can rewrite this for different forms, optimize it for different forms or quantities, just depending on your exact system that you're using. So if for different courses and different classes and different applications where people use Bernoulli, it's very common to see them rewrite it for different applications. Maybe if you're using a system that you do a lot of pressure units, maybe you'd rewrite it not in terms of height, but in terms of pressure units and such. But anyway. Now, here, so if I was optimizing it for pressure, I would maybe have just a P1 here and not a P1 over gamma. This one is kind of optimized for height. Someone asked me a question over the weekend, which is, what is pressure head? Pressure head fundamentally is looking at the pressure in a system expressed as a height in feet, or in meters, or in any other kind of height. Just as we discussed previously, how the pressure we can conceptualize pressure as the ability of a gas at that pressure to raise a column of liquid, either water, mercury, etc., to a certain height. That is just a different way of expressing pressure. Okay, and again, let's review the assumptions here. Some of the assumptions of Bernoulli. Well, I don't necessarily need to write all of them out, but the important ones mainly are no energy is lost. Or gained, actually, as well. So this means no pumps. Most of the assumptions can be boiled down to really just no energy is lost or gained. No pumps, turbines, friction, etc. Also, we're dealing with an incompressible fluid. The Bernoulli equation is assuming that volume is constant, so an incompressible fluid, and that's the general idea. So we could boil the energy assumption down into talking about viscosity and things like that. But really, the important things to keep in mind is that this represents energy. Bernoulli is all about energy. and we're talking about an idealized fluid, it's very much, this is very much equivalent. This is the fluid's equivalent to, if you remember back to your fundamental physics, high school physics, something like that, this is equivalent to a problem of something like projectile motion or a simple energy problem where you're, like for example, if I were to use a physics example, I could use the famous roller coaster problem, like where you have a cart at the top of a hill, and we're not going to work through this example all the way, but just if you remember problems like this, I could draw a really complicated track, and I could have point A and point B, and it's released from rest here. It goes through all these loops and then says, what is the velocity at point B? Remember this type of problem from physics? This is an energy method problem. Energy method problem in physics. Problems in physics. Example would be a roller coaster. And the way you analyze these is very, very similar to Bernoulli. You say, in that we don't have pressure in this case, in this system, but we say like mechanical energy 1 equals mechanical energy 2, PE plus KE1 equals PE plus KE2. So the total mechanical energy at the start is equal to the total mechanical energy at the end. There's a few things about this. We don't actually need to analyze it at every point along the way. We simply say it's path independent, which means that all that matters is the beginning state and the end state. If energy is conserved, it doesn't matter what it does between here and here. Now, if I asked how long it takes to go from here to here, well, then it's not path independent anymore. But if all I'm asking is what the velocity is at this far end point, as long as I know that it starts from rest here, I know its initial height and its final height, it's trivial to find the final velocity. So path independent, I don't care what kind of crazy loops it's doing in between. I don't need to know the height or the radius of these curves. I don't need to know any of that. If you ask me to model it and say, okay, what is the velocity at time equals 2 seconds or something more specific like that, sure. Then I'll actually need to know I'll need to know specific details about, the width of the tracks and the radius of the tracks and all sorts of fun, really complicated things like this. And we could make this problem as complicated as we wanted to. But the basic idea is, as long as it's something like this, a simple energy method problem, it is path independent. And again, energy is only converted. Energy is only converted, not gained or lost. And the reason I'm mentioning this is not that it's important to review elementary physics, but it's important to keep in mind is that Bernoulli is like this type of problem. Bernoulli is very much analogous to this type of problem. Now, we will later see that we can add terms to the Bernoulli equation, taking into account things like pipe losses and pipe friction and that kind of thing. But the pure Bernoulli equation that we have worked with before, without any kind of losses or turbines or pumps, it is equivalent to this type of system. They are one and the same. So again, the very same assumptions are applying. Here, you usually assume a frictionless track. We're saying there is no rolling resistance in the axle of the cart. There's no friction between the wheels of the cart and the track. There's no air resistance. Basically, we're dealing with a highly idealized system that no energy is ever lost from. In other words, if this thing were to loop back on itself, and if the track actually went in a complete circle, based on the assumptions of this problem, this thing would literally just keep going forever, considering the assumptions of what I'm working with. Now, we know systems in real life can't behave this way, but really that doesn't matter. For certain applications, for certain bounds, for certain low enough velocities, things like that, these assumptions are actually perfectly valid. They will always be off by a small amount, but for certain systems of limited range, this can actually be a very useful problem, or a very useful solution, or assumption, I should say. And I will just mention one other thing before we move on to some examples. One final bit of information that we will use is our continuity of flow equation, which says that our volumetric flow rate 1 is going to be equal to our volumetric flow rate 2. Or in other words, V1 A1 is equal to V2 A2. Volumetric flow rate, even as we go through change in diameters, etc., is going to be constant. So no matter what we assume, no matter how we set up our equations, regardless of pressures and velocities, etc., the flow rate has to remain constant. Flow rate has to remain constant. So interestingly enough, that V1A1 does introduce an interesting type of restriction. So I don't know if I necessarily want to work all the way through a problem like this, but let's say I had a pipe with a constant diameter here. Let's say I had a pipe with a constant diameter, and it's at an angle. How would this affect it? Say there was an A1 and an A2, and maybe here the fluid is flowing up. Maybe here there's V1, and here there's V2. And here there's P1 and H1, the pressure one and the height one, or let me say Z1 perhaps. And here there's P2 and Z2. So pressure 1, pressure 2, height 1, height 2. Now, if we go back to our Bernoulli equation, P1 over gamma plus V1 squared over 2G plus Z1 is equal to P2 over gamma plus V2 squared over 2G plus Z2. And let's say I'm given, I don't know, let's say I'm given P1, Z1, and Z2, find P2. Well, how would I do this? Now, at one point it's tempting. It's very tempting to look at this and say, oh, well, it's going to a higher elevation, so I would expect the velocity to be lower. Just like if I throw a ball straight upward in the air, I expect its velocity to be lower as it's rising. But the continuity equation actually produces a very interesting limitation on this. See, because the pipe diameter is constant, the velocities have to be the same. Continuity demands that V1 equal V2. Because if Q1 equals Q2 and V1 A1 equals V2 A2, well, if these cancel out because they're the same, then V1 has to equal V2. Oh, so V1 has to be equal to V2. So the problem with this, of course, is that this thing is going to higher elevation. The fluid is clearly it's raising up. This is, I'm doing this qualitatively, so I'm not giving exact numbers, but point 2 is actually at a higher elevation than point 1. So this fluid is gaining gravitational potential energy as it rises. And so what we can see then, if these two terms are going to drop away, if V1 is equal to V2, then these two terms cancel out. So therefore, what this reduces to then is P1 over gamma plus Z1 is equal to P2 over gamma plus Z2. And again, we come back to fundamental energy. What's going to happen here is the energy, this Z1 is going to be less than Z2. Z2 is greater than Z1. This thing is going to gain gravitational potential energy. A particle of fluid, as it goes from 1 to 2, is going to gain gravitational potential energy. And that energy cannot come out of nowhere. We cannot create energy ex nihilo, right? It has to come from somewhere. We cannot get something for nothing. And where this is going to come from, if this Z2 is greater than Z1, P2 must be less than P1. The mathematics demands it. Z2 greater than Z1, therefore P2 is less than P1. So in other words, this is very similar to what we would have, say, in a building, or a pipe system in a building. I'll draw that out following this. We are giving gravitational potential energy to the fluid, and so it must, that energy has to come from somewhere, and where it's going to come from is the pressure in the fluid. So in other words, if you have a building, say a mini-story building, something like this with the ground here, and I don't know, we have several stories here, and there is pressure from the mains coming in, the water mains coming in, and then there's risers to carry the fluid, or to carry the water up to the different floors. There'll be risers to carry the fluid up to different floors, etc. If I can manage to draw pipes correctly. And then at each level there'll be taps, there'll be toilets, there'll be faucets, there'll be showers depending on the building type, all of the places that we access water for our daily use. Now, here again, so there'll be, P1, there'll be a P2, P3, P4, P5, etc. Now, while it's in the pipes, while water is in pipes, and so maybe this is and maybe down here you have just at the pipe level, the ground pipe level, maybe P naught here. This is the pressure of the pipe through the entire neighborhood or something. While stationary in the pipe, P1 will be greater than P2, will be greater than P3, will be greater than P4, will be greater than P5. They must be equal. The different pressures will be equal. Or sorry, they must be unequal. Sorry about that. They will increase. They will decrease as they go higher. So the pressures at the higher level will be less and less and less and less. Does that make sense? Again, because what's going to happen is you have to force the fluid higher and higher, and you're going to be trading. You're going to be trading height for pressure. Let's look at another instance here. Okay, so let's think about something here. I'm going to do another qualitative example here, and this is going to be an interesting one. What about when a fluid actually exits a pipe? Say a sink faucet. So here's the interesting thing. We're going to have a column of fluid. It's going to, water is going to come out of the tap and then fall downward. So say you have point 1 here and point 2 here. Actually, just let me say 1 and 2 here. Don't have too many P's on the board. Now, the interesting thing about this is both of these are at atmospheric pressure. P1 is equal to 0 in terms of gauge pressure anyway. I'm doing this in terms of gauge pressure. P2 is equal to 0. And here, let's say also that Z2, we have Z1 and Z2 and V1 and V2. So the pressure here is going to be constant. So here we can't trade pressure for anything. Everything is forced to be at air pressure because it's at atmospheric pressure. It's surrounded by the atmosphere. So let's go back to Bernoulli. Again, P1 over gamma here plus V1 squared over 2G plus Z1 equals P2 over gamma plus V2 squared over 2G plus Z2. Now, so in this case, the pressure terms are going to cancel out. Those go away. And clearly, this is not difficult to see, that since Z1 is greater than Z2, then V2 is going to be greater than V1. That is not difficult to conceptualize. However, we still have to, even though this is not in a pipe, we still have to worry about our continuity equation. Because at least at relatively low velocities, when you have water just like absolutely streaming out of a pipe, it doesn't maintain a nice sort of pipe-like shape. But water, if it's at a relatively low velocity, likes to stick together. It's that surface tension thing. It's sort of, if it's not in a pipe, it'll actually kind of form a pipe of itself. It just bound together by its own intermolecular forces. For a small enough flow rate, for a small enough diameter, for a low enough velocity, you've seen this. It will actually form a kind of shape all on its own, held together, sort of a virtual pipe, held together by its own internal cohesive forces. So here we still have V1A1 equals V2A2. So if we know that V2 is greater than V1, so we're not going to have the constant velocity anymore, but we still need to maintain constant flow rate. And the way we do this is, oh look, if this thing over here is bigger than this, then this thing has to be smaller to balance the equation. Therefore, A2 must be less than A1. And if you've never noticed this before, I suggest you go home and when you get home tonight or you're in the bathroom or something here at school or something, well, you might get some weird looks. I don't think you can do the restrooms here. They might have one of those aerators or something. You don't need a low flow faucet. You need something without an aerator on it. You need something you can get a nice clean stream out of. But if you look closely, what they tend to do is they do something like this. The stream of water gets thinner as it gets further and further away from the faucet. This is not accidental. I don't know if you've ever noticed this before, but if you haven't, I suggest you go and take a look at your faucet at home and just, open the tap and stare at it for a few hours. Well, hopefully it doesn't take a few hours, but, don't call the water conservation people and report me, but anyway. This is a very simple application of Bernoulli's equation and the continuity of flow. The pressure is going to be the same here and here. It has to be. Everything's at air pressure. But velocity also has to increase, or actually I should say, even if velocity doesn't increase, gravitational potential energy has to decrease. And so it's falling water. The velocity is the gravitational potential energy is decreasing from here to here. That energy has to go somewhere. It can't just disappear into the void. And so where it goes is into giving the fluid greater velocity. And then it's going to giving the fluid greater velocity, and then in turn, in order to preserve the continuity of flow, the continuity of flow rate Q, the velocity has to increase as it falls. And as the velocity will increase because of Bernoulli, but in order to keep the continuity of flow conserved, the cross-sectional area must decrease. Again, the reason water just flows like this, like for some fluid for a fluid with very low internal cohesive forces, it wouldn't necessarily have to do this. It could just turn into like a spray or a foam or something. And in fact, water at very high velocities, that's what it tends to do. Instead of forming a nice, clean, cohesive flow like this, it tends to just bubble and flow and boil and things like that. A roiling, churning kind of turbulent flow. And later in the semester, we will actually learn the difference between laminar and turbulent flow. But anyway, now, interesting question. So I just mentioned that the velocity has to increase as it drops because of conservation of energy. But here's a question. Something else that we might consider. Lots of qualitative, interesting thought experiment problems today. What happens if this is emptying into a bowl, a sink, or other vessel? So, interesting question. The water this time is flowing into a large pool of water. The question then So the water flows down, it gains velocity, it strikes the water, and then it stops. It's gone from, where did that energy go is my question. Where did the energy go? Well, it can't really go to pressure. That was one suggestion. It can go to pressure. Perhaps a little bit.
Raising the height.
It might. So I don't really want to say it's going to pressure, because if we modeled this simply, we might say that, oh, this, as water falls down here, this isn't true. It does obviously mix, but one way to conceive of this would be to say, oh, let's just say each layer of water just like piles on top of the existing surface of the water. So if that was the case, and that's a way to sort of to simply conceptualize it. Imagine if this bit of water just adds another layer on top, the next bit of water adds another layer here, et cetera, et cetera. That would be one way to sort of conceptualize it. But then the energy of that water, the potential and kinetic would just seem to disappear. So where does all that energy go? Any ideas? Sound would be one suggestion. Yes. So it's going to be lost to the environment. This is a case where Bernoulli no longer applies, and mainly where 90% of it is going to end up is it ends up as heat. In fact, that's usually the answer for a lot of our things in civil and mechanical engineering. When energy tends to disappear, it ultimately ends up as heat. In fact, if that's another way to think about that. Like in terms of conservation of energy, if you think of an automobile, ultimately every gram of gasoline that you burn ends up heating the atmosphere and the road and everything else, doesn't it? Every drop of, basically, on an almost universal level, with very few exceptions, every drop of gasoline we burn, every bit of coal we burn, every watt of solar power or wind power we collect, every single electron volts of nuclear energy we release when in reactors, basically all of it ultimately ends up as heat. We use it for a while, we use it for various processes, we use it to create things and mill things and power things and propel things and light things and do a million different things with all the different ways we have of using energy. But basically, ultimately, all of it ends up as heat. It all ends up basically in the atmosphere eventually as heat. Now, this isn't really the problem of global warming. Global warming is something very different. Global warming is where you're actually changing the chemical properties of the atmosphere, making it more opaque to infrared radiation. That's what's producing the overall global warming effect. But if you really start looking forward to some, I always like this. I always like looking at the idea of the raw heat output of things. It's kind of cool. And in fact, if you actually work the numbers on it, an interesting thing happens. Like if you now, theoretically, there is if you start looking at the far future and potential technologies and things like that, you can sort of conceive ways to get around other limits of like living space requirements and food and things like that. If you have a high enough technology, so for example, if you invented fusion reactors or something, you can start growing food indoors, and growing food in greenhouses and deserts and doing all sorts of things that you could really increase the carrying capacity of the planet. You could theoretically, with enough technology, you could support a population of trillions on a planet like the Earth, if you had enough technology and properly deployed it, etc. And you could even do that without destroying the environment if you did it properly. But interestingly, I really like thinking things in terms of heat, because if you really look in the far future in terms of projecting human populations and machines and things like that, ultimately the real hard barrier in terms of how advanced your civilization can get or how many people you can support on your planet is heat. Because you can get around all of the other requirements via just sufficiently advanced technology, but the one thing you can never get around is the raw heat output of all of your machines and people and everything else, primarily your machines. So because the planet is, of course, surrounded by a vacuum, and vacuum is the best insulator there is. And the only way the planet can ever get rid of heat is via radiation, just glowing, essentially, in the infrared bands. And so if your civilization starts outputting more and more and more and more and more heat, eventually that heat gets so large that it would actually cook the people on the planet and make the planet uninhabitable. Now, you need a very, very high population before this ever could be a problem. You need populations in the trillions before this ever becomes a design consideration. But if you start looking at sci-fi scenarios of the very far future, the raw heat output of the civilization actually becomes the defining limiting point of how many people you can support on a planet. But anyway, that has something to do with fluid mechanics, but not as much as you might think. Okay, anyway, that was, pardon my digressions. Okay, so I have a couple more examples that I might like to work through here. Okay, so let's work through this, continue through. Maybe we won't get out of here early, but okay. So, sorry, I just felt like extrapolating. So given, let's see, consider the loon, also known as your professor. Consider the loon. Not loon, not loom, loon. Consider the common loon, which is an aquatic bird. An aquatic bird known to inhabit certain aquatic biomes, I guess. And what I want to say then is, and I'll also say I want to find, so we're given that we're dealing with a bird, and find the swimming velocity needed So this is a cool application of Bernoulli because it's producing things that you might otherwise think of, producing things that you might not otherwise consider. Velocity needed to produce the same dynamic pressure This is an application of Bernoulli that you never really would have considered. Swimming velocity needed to produce the same dynamic pressure as when it flies at, say, let's do 40 miles per hour. Okay. So here, let's consider this. Now, this term, if you remember from Bernoulli, we had the term v squared over 2g, right? And sometimes this is referred to as dynamic pressure. Sometimes this is referred to as dynamic pressure because, again, it's another way to conceptualize Bernoulli is if we think of everything in terms of pressure. And we can actually think of velocity in terms of pressure as well. Basically, this is saying is, when I talk about dynamic pressure, what I am saying is what pressure is this equivalent to? In other words, the energy represented by this velocity of a fluid, what pressure would it take to have that same kind of energy? I'm looking at equivalence, okay? Or another way to look at this is 1/2 rho v squared, as we'll see when we work with drag later in the semester. Actually, I tend to work through, but actually it tends to be the last thing we look at in the final unit of the semester, drag. Okay, so basically here I'm not really doing a full Bernoulli, I'm just sort of relating the pressure, I'm just sort of reconceptualizing velocity as pressure here. And the pressure, basically I'm saying, okay, this bird is capable of moving in two ways. It can either fly or it can swim. I suppose it can walk too. But its two main ways of locomotion, it can either, it's sort of like a penguin, well, penguins can't fly, never mind. It can move in two ways. It can swim under the water, or it can fly above the water or above the land. It's sort of a universal bird, you might say. That'd be really weird. Anyway, so let's compare the two. So I'm going to have 1/2 rho v squared for air, and this is going to be equal to 1/2 rho v squared for water. All right, and then the 1/2 will nicely cancel out, so we don't need to worry about that. That will nicely cancel out. And I can simply, by very basic algebra, find that v water is going to be equal to rho air divided by rho water to the 1/2 power, or just the square root of that. times the velocity of air. Make clear that the square root is not, the v is not in the square root. Times the velocity of air. Just times the velocity of air here. And then that's going to be, let's see. I'm going to use just, you can use whatever density of water is, whatever density units are convenient, but I have them handy for slugs. 2.38 times 10 to the negative 3 slugs per cubic foot. It really doesn't matter what we use, it's going to cancel out anyway. Divided by 1.94 times just 1.94 slugs per cubic foot for the water. This to the 1/2 power times 40 miles per hour. And this in turn will then equal, if you run through the math, you'll get 1.4 miles per hour. So notice the format I'm using. I'm trying to stick to this sort of given, find, and I could probably even include the 40 miles per hour in the given, and then finally box my final final result. Questions on that? Okay, hopefully fairly straightforward, and then maybe we'll work through one more example. This one a fairly straightforward pipe example. Okay, here, let's say I have a pipe that is undergoing a change in elevation and a change in diameter. So let's say I just, have a big combined system. I'm just going to look at everything. So now nothing will cancel out. Everything's going to be changing. So this is really sort of the hardest case of Bernoulli, at least for the simple Bernoulli that we're working with currently. Okay, so there's going to be a change in diameter. We have 0.1 and 0.2. And then I'm going to have a datum line, which is just my reference line. And the elevations here, this is going to be 4 feet, and this is going to be, let's say 10.70 feet. 10.7 feet here. And then here, some pressures and areas. Let's say P1 is 65 psi, and D1 is 6 inches. And I'm also told that Q1, the flow in, is 2.08 cubic feet per second, which also means that Q2 is equal to the same thing. Assuming as long as the fluid is incompressible, I immediately know that the flow rate over here is also 2.08 cubic feet per second. I can change area, I can trade area for velocity, but flow rate, at least for an incompressible fluid, is going to remain constant. And here, I'm going to say that I have P2 equals, and actually that's what I'm going to be finding. Sorry, I'm going to be finding P2. And I will say D2 is 2.08. Oh, sorry, that's not right. D2 is 9 inches. So we're starting with a pipe with a diameter of 6 inches. We're going to a pipe with a diameter of 9 inches. We have the flow rate constant, and the height is also changing. So now everything is changing all at once. We don't just have we don't have a very simple trading one variable for another. We have a complete exchange between the different forms of energy. So this one is a bit more complicated than the previous things we've looked at. And there's one other thing that I need that I've been given, and this is that this thing is full of oil. Just to make it even more difficult, we're not dealing with water, we're dealing with oil. And I am told that the row of oil is going to be 0.84 row of water. In other words, this fluid, this oil, has a specific gravity of 0.84. So, loads of fun. Yes. Now, so solution.
What?
So again, recall. So first thing I'm going to do is I'm going to find the velocity. Q equals VA here. And V1 equals Q1 over A1. And in this class a lot, I'm going to use the pi over 4 d squared for area a lot. Area equals pi over 4 diameter squared. 2.08 cubic feet per second. 2 cubic feet per second divided by pi over 4. And I am just going to right away convert from inches to feet. 6 over 12 feet quantity squared, and this will come to 10.59 feet per second. So that's our velocity at point 1. And then V2 is going to be equal to Q2 over A2, which is the same flow rate, 2.08 cubic feet per second, over pi over 4 times 6 times 9 over 12 feet to the third, feet squared. Oh, what's the order of magnitude among friends? Squared third, same thing, right? Oh, a math joke. Bad math joke. And this comes to 4.71 feet per second. Okay, now I need to, on the next slide, plug these into the Bernoulli equation. I'm going to plug these into the Bernoulli equation. And I'm going to use, let's see, the appropriate pressures here of pounds per square inch. So just running through Bernoulli, I'll have 65 PSI, pounds per square inch, times 144. Now here's the tricky part. Watch out for your conversions. Inches squared per feet squared, or square foot. If I'm going to do this all in feet, I need to use consistent units. Times 0.84 times 62.4 pounds per cubic foot. So basically I'm doing all this in pounds and feet. So again, this is the specific gravity, and 62.4 pounds per cubic foot is the density, or I should say the specific weight of water. Plus 10.59 feet per second squared, divided by 2 times 32.2 feet per second squared. That is the acceleration due to gravity in English units, plus 10.70 feet. That's the height of the original point 1. And this is then going to equal P2 divided by 0.84 times, again, 32.2. So again, this is our unknown. 0.84 times 62.4 pounds per cubic feet. Don't worry, we're almost done. Plus 4.71 feet per second squared, divided by 0.84. Oh, sorry about that. We keep writing the wrong thing down. Times 2 times 32.2, just 2g here, feet per second squared, plus 4 feet here. And that is the full written out form of Bernoulli with inputs in place. And then from there, it's just simple algebra, which I'm sure you're capable of, and I'll leave that as an exercise to the reader. That's a famous, dangerous saying, which comes to 9784 pounds per square foot, or 67.9 psi. And then I will just summarize by saying the pressure at point 2 is 67.9 pounds per square inch, and I'll put a box around it to emphasize that this is my final result. And that is a complete application of Bernoulli, working through all of the, working through cases where everything is changing, etc., etc., etc. All right, that'll do it for today. If you have any questions, feel free to come see me in office hours, send me an email. All right, so that'll conclude we'll maybe work a bit more with Bernoulli on Wednesday, but then we'll move on to some new material. So thank you for watching, and as always, thank you.